Hello and welcome to this new tutorial called Ensemble Docking. I mentioned previously in a video that I'll be doing this ensemble docking from MD simulation with the static molecular docking software called AutoDock Vina. So this is the protein that I simulated for almost 2 microseconds, and this is a pentameric protein. And this is the same example that I have shown previously in my video, which was in protein membrane simulation. Okay, and I have simulated it for 2 microseconds. Okay, and I want to perform now the ensemble docking, which is generating a series of conformations of this particular protein from the MD simulation results. Okay, so the things that you require is XTC file, the TPR file, and I think input.pdp or input.gro file. Those are the files that you require, and have prepared a script as well. So this is the script where you can extract the protein structure, because my protein was embedded in a lipid membrane. So I have to only extract the proteins, not with the ligands or not with the lipids. So just it has to be protein. So first you make a directory, and then you provide all these commands, which is the interval that I require is 100 nanoseconds. So per se, I have done this for 1 microsecond. Actually, I've done it for 2 microseconds, but per se, I have done it for 1 microsecond. Then you need intervals from 100 nanoseconds. Okay. And by utilizing this particular script, what you have to do is you have to input this for loop, and the basic command is GMX trjcon, which is the trajectory conversion, and you provide the XTC file and the input.gro file. But in this, I have selected echo 1. That means the group 1 is selected only with the protein. You can select group 2 as well, or you can take only the backbone, but backbone is nothing more beneficial in molecular docking because you require the side chains. So that's why group 1 has to be selected. That is the protein. And it will take a little bit of time, and it will generate a series of conformations like 100 nanoseconds, 200 nanoseconds, 300 nanoseconds, up until whatever the timeline that you have done the MD simulation for. Okay. So this is the structure, and if you load another 200 nanoseconds into it, so it will, you can see the conformations, the conformational chains between 100 nanosecond and 200 nanoseconds. And also, if you load another 300 nanoseconds, it will show even more conformational samplings. Okay. So 300 nanoseconds, it's still generating. So it takes some time, depending on your simulation, depending on your protein. If your protein size is too big, it will take more time. But if you have a small protein, it can generate easily within a couple of minutes. So now I have loaded these 3 conformational samplings: 100 nanosecond, 200 nanoseconds, and 300 nanoseconds. And I want to look into a specific residue. For instance, I take this valine residue. Okay. And I just want to compare it with the 100 nanoseconds to 200 to 300 nanoseconds, just to see how the conformational sampling of that particular side chain has been done. Basically, whatever the commercial softwares like Schrödinger and Discovery Studio, they also do the same with their protocols. So you don't need flexibility, because the flexibility that you are getting from MD simulation is more than enough than actually doing a static docking with the flexible receptors, where you rotate the rotamers or the side chains based on that. But it's a real simulation that you have performed already, and you don't need to perform flexible docking. So now on this MD simulation, what you can do is you can perform the static docking, because you have generated already the flexible residues or the flexible conformations of the protein by using GROMACS, AMBER, NAND, or whatever the softwares that you use. So this is called conformational sampling. So these are the series of the files that will be generated. And yeah, now we can perform the static docking. So I'm going to stop here because I don't want it to run for a longer time. I don't want to waste the time. So I'm just showing you again the script so that you can take a snapshot or a screenshot or copy it. Also, I will provide in the description as well. So yeah, this is the way that you generate a series of confirmation. And this is called conformational sampling. I think you might have heard about this. And also many of the protocols from GROMACS, they also provide this sampling feature, like umbrella sampling, or maybe you perform any steered MD calculation or ensemble sampling. There you can also get all these PDB snapshots. Even if you perform a normal MD, that's also fine. Okay. So I have already generated all these confirmations before. So it's called protein snapshots, and I have taken 600 to 1000 nanoseconds. For instance, you can take from 0 to 100 or whatever the confirmation that you feel like that it's ready for the docking. Okay. So yeah. So let's go back. So I'm stopping here, and let's go back to the ensemble docking procedure where you require some of the files. The first one is the protein snapshots. Okay. And then you require the Vina executable file. And this is the script that I have written, ensemble docking script.sh. And the first and foremost thing is the Vina executable, where you can download from AutoDock Vina website. It's a executable file for the Linux, or maybe you have been using Mac or Windows. Whatever it is, you can download this. And the next thing that you require is your prepare receptor 4.py. This is the file that you get from the MGL tools installation. You go to the MGL tools, then you go to the AutoDock tools, and then you go to the utilities 24, where you can exactly get this script from, which is called prepare receptor 4.py. Or if you don't have this, then we have this latest tool called Miko, where you find this make prepare ligand .py or make prepare receptor.py file. That's from the Miko installation. There also you can get the same, but this is the directory where you get your files, which is prepare receptor 4.py. And also you can use the prepare ligand 4.py as well, but Miko is much more beneficial because that's the file that I think many people are using right now for AutoDock Vina. So you can take that, and you can I have installed it already. So you can find where the script is installed by using a command line called which, and then you type in the file name where you have installed, and it will tell you the directory where your this particular package has been installed or particular script has been installed. So it's in my pymol directory. So if I go there, I will find this make prepare ligand.py. So you can give this a particular link to the script, or you can copy paste this particular script into the directory so that it can find, so that the script can be executed from the directory itself, or else you provide the link, whatever you feel like. Okay. So this is the script from the Miko, as I mentioned. You can go to the Miko and download this particular script, or you can install it via pip install Miko or Conda packages also. So this is the GitHub repository for the Miko, and this is the interface for the AutoDock. So you can utilize this, and the command is make prepare ligand.py. You provide the SDF file. It will convert the SDF file into PDBQt file. Similar way, you can also run it for receptor as well. Okay. So now we can go back, and yeah, the next thing that you require is the ligands file, where you have your SDF file ligands, the script will automatically convert the SDF file into PDBQT file. And then if you go to the script, I will show you what are the things that I have written here. I mean, you can easily prepare this script by using any sort of AI-based tools. So first is the directory path, which are the protein snapshots, your ligands directory. Output directory will be docking results, Vina configs, protein PDBQT, ligand PDBQT will be generated. And you provide the center X, center Y, and center Z, size, exhaustiveness. You can keep it to 8 if you have 4 CPUs, or maybe make it to 16 or 128, whatever you feel like. And number of modes is 9, which is the default one. And you provide the Vina executable with all the links to the prepare receptor 4.py and make prepare ligand.py. So yeah, and then these are some of the functions, Python functions, where you can create the proteins and the ligands as well. But and this is the function for the run docking, where you can perform parallel docking as well as you can perform a single docking as well. So this is the script that I will provide to you. And if you want to install all these packages for the plotting and stuff or Vina installation, you can use this Conda environment, and you can install this Conda packages. So now I'm going to execute this Ensemble docking with these protein snapshots, where it will generate a series of conformations of the ligand docking to the protein, and it will execute in a well-mannered fashion, starting from the protein preparation for the ligand to the ligand, and then finally generating the Vina config files, and also the final thing is your docking. Okay, so you execute the script, and it will run basically by checking the requirements, whether the requirement checks are completed or not, and then converts your protein PDB files into PDBQT, which is in the directory protein PDBQT. Now you can see your PDB files are converted into PDBQT files. Okay, and the next thing that will be done, and the next thing will be the ligand SDF file, which will be converted to the PDBQT file. So it will populate in a bit. Now you can see the PDBQT files have been generated, and then the Vina configs have been generated already. So you can see that this is your center X and Y, whatever you have provided in the script, and the results will be your doc ligands, ligand 2, ligand 1, ligand 3, or any number of ligands that you can provide. Okay, so it will take some time depending on the size of the protein, the binding site that you have provided. If it is big, then it might take some time, and if you increase the exhaustiveness to 128 or maybe 32, something like that, it is also going to take some time. And these are the log files that will be created. Now you see this one is generating right now, but you can see this one has been completed with the Affinity, with the RMSD, the typical AutoDock Vina input output file, right? So in this way, it will generate a series of conformations along with your structure files, which are the docked PDBQT files. And you can see my binding site was only for the tutorial purpose, so that you can specify a smaller binding site where exactly your binding site is. This is only for the tutorial purpose, so that's why I'm not focused on the binding site itself. But you can see how since my binding site is bigger, that's why my ligands are scattered all over the protein. So it has to be pinpoint to a particular binding site. And you can see this is the best score, which is how the experimental structure looks like. So yeah, AutoDock Vina is good unless you provide the flexible docking sampling, from your MD simulation. Then it can generate exactly what you need for your conformations. I mean, many people use AutoDock Vina for the calculations, I know, but they stick to the static one, which is not good, I would say. So please use this approach, which is called ensemble approach, which is much more beneficial in order to sample all your conformations. And this will also generate a CSV file with your binding scores. And finally, it will generate a plot that will be much more beneficial when you want to overlook all your results. You don't want to go one by one, but you want to overlook all your results, then you can see that. Okay. And these plotting files will be is written here. I have used matplotlib and Seaborn, but you can use whatever the libraries that you have. So I'm going to make another video regarding all these plotting functions, so that it'll be easy for you once you get the docking results or MD simulation results, how you can plot those. So that also I'm going to make one video about that. So yeah, so it's generating right now. It will take some time, and yeah, I think it's completed now. So your docking has been completed and your results have been saved to docking results. And the best one is your affinity, which is minus 8.7 kilocalories per mole. That is protein 800 nanoseconds. Okay. So when you open the docking results, you have these two plots. One is the PNG file, another one is the PDF file. As you can see here, these are the distribution of the binding affinities, your ensemble docking analysis, affinity by the protein with the protein snapshot, and your binding affinity kilocalories per mole. That's a box plot. And also you have these binding affinity plots as well. Okay, and this particular heat map is where you can see all your binding affinities. These are basically the same plot, but in a different way. So you can, get these um, plots, and also a CSV file with all your scorings. I have prepared a script actually, which is called plotting.py. So basically, it requires your matplotlib, not Prodi and Vina, but matplotlib, Seaborn, etc. And you can create the environment by using or contact create your environment name, and you provide the channel name and all your libraries like matplotlib, Seaborn, pandas, numpy, scipy, etc. So it will install all of them. I think I have installed it already. I couldn't find earlier, but anyway, so you can install all these packages. So once you have installed this, then you can execute this plotting.py by the command line called the Python plotting.py. And if you write -h, it will tell you exactly how to plot this function. So you activate this, activate my environment, and then utilize this particular script called plotting.py. And you have to provide the results directory, which is the docking results. So yeah, and then there will be a plot PNG file, and that will give you an overview of the docking results that has been performed. I mean, it's similar to the plot that already generated, but it also gives you a heat map and a very nice violin plot along with the docking scores. And also it will give you a consensus binding analysis and mean affinity plot as well. So it's basically the plotting functions that you get. So nothing rocket science in here. And if you want to look for the results, the PDBQT file that is actually generated all your poses, you can also do that. And this is the plotting script file. I can provide you all these scripting files so that you can run easily. This is the docking results that we are going to investigate. So you can load, I think, 600 nanoseconds or maybe 800 nanoseconds PDBQT file, and let's see how the docking results look like um, of the highest binding affinity, which is minus 8.7 as it was predicted. So you can load all of them together, and you can see here you have this minus 8.7 scoring. This is minus 6.7, this is minus 8.7, and you can pinpoint that particular, and you can refer from the plotting as well. So minus 8.70, which is your protein 800 nanoseconds plus your ligand 4. Okay. So you can delete that, and you can, yeah, get the ligand 4 minus 8.7, and this is your basically the final ligand. Out of all the conformations of these 4 ligands, this one turned out to be the highest one with that particular binding site. And I think in this way you can sample the conformation, and you can predict that whether the flexibility of the amino acid residues during the MD simulation perfectly fits this particular ligand into the binding site, and I think that will be your optimal results to check. Yeah, so that's it, and I think I will provide the script in the description, or maybe I will put it in my GitHub channel, so you can look for the GitHub channel as well. So yeah, thank you very much. I hope you enjoy watching my videos, and please subscribe to my channel. Thanks very much.